Okay, time to switch to the fifth technology field, which is compound materials. And thank you very much, Walter, for presenting, SiC materials for power technologies.
Ça marche? Thanks for the introduction. So it's a pleasure for me to come here and present this work developed in Soitec with the partnership of our colleagues in CLET. So I will discuss engineering SiC materials for the power technology. So one slide as an agenda. First, why we are doing engineering SiC substrates, and what is the proposal from Soitec regarding what we call SmartSiC substrates, and a few data, how do we made it, and what are the results, focusing on two main characteristics of our materials: electrical resistivity, which is key for power applications, and the crystal quality. And then to conclude, pictures on the demonstration of 200 millimeters product. So, why? We have for power applications, we have a very high demand for SiC. SiC will address a large band of product. We could divide in two parts: the medium voltage. No, pas. Medium voltage, we've already several applications in the medical, in the engines, and one key point, which is electrical vehicles and hybrid vehicles. But even some very high voltage, more than 1,700 volts, with especially in the rail applications and in the solar industry. But the market is driven now mostly by the electrical vehicles. Also, SiC materials is proposed to improve the power electronics performance. And since 30 years, the industry has already demonstrated a very significant improvement. One point for SiC materials is we increase the size of the materials. 3 decades ago, it was few tenths of millimeters in diameter. Now we have 200 millimeters product. Also in quality, micropipe is an issue for device performance and device reliability, and we have several decades of improvement in 30 years. And the demands in parallel increase strongly, mostly pushed by the electrical vehicles demands. So this market is growing, but we still have some key challenge. One of the challenge is the quality. Defect in the materials coming from the material itself or from the device preparations. The epitaxy process, as an example, will have an impact on the reliability of the device. Cost, SiC is quite expensive. And scalability, okay, you can have some nice announcements of 200 millimeters SiC product, but it's still quite rare. And if we could multiply such kind of materials, it would be of a great opportunity. So, thanks to the Smart Cut, we will address these three key challenges: to have a high quality product, to have interesting cost improvement, and to be scalable, pushing the 200 millimeters adoptions. So what is the proposals? The proposals is, we call it SmartSiC substrates. If we compare with a bulk, when you buy a bulk SiC, you need then to have some conversion, to create some conversion buffer layers, you need to create an EP layers, then build your device. With SmartSiC, we will associate ultra prime thin layers supporting your AP and device on the ultra high conductivity SiC product, typically poly SiC. So it will give a unique value propositions, improving the yield, improving the resistivity, simplifying the AP process, and improving the adoptions for 200 millimeters. So we define two products. One we call it SmartSiC Performance, the second SmartSiC Advanced. SmartSiC Performance is currently in sampling mode. We deliver some wafers to customers. They are evaluating the wafers and engaging already the qualification flow. SmartSiC Advanced is still in engineering, so we are still under evaluation by the customer. What is similar between the two products is, as the handle materials, we have a ultra-low resistivity, less than 5 million centimeters, typically a factor of 10 improvement in the resistivity versus a conventional mono SiC. So a strong improvement in the electrical performance. On top of this ultra-high conductivity wafers, we transfer a thin layers of mono SiC, prime quality mono SiC for SmartSiC Performance, and even a BPD-free single crystal for the SmartSiC Advanced. How do we do it? SmartSiC, it's smart cut technology on SiC. So these, maybe you already seen these the smart cut schematics, because that's common on all our SOI product. We develop smart cut since more than 30 years, and we are in high volume production for many other products. When we apply to the SiC, what do we need? We need two wafers, one donor, 100 wafers. Donor wafers is a prime quality conventional mono SiC. 100 wafers is, I already mentioned, it's a low resistivity poly SiC wafers. Surface preparation, smart cut implant, just to create a thin cleavage layers, and then conductive bonding. That's key. We will have a conductive bonding, we will have a perfectly conductive bonding interface. Then splitting and finishing. Finishing with high temperature annealings, CMP, so we will have an AP-ready surface. The wafers can enter in the production lines and go directly to AP. And after the splitting, part of the donor wafers is still here. We can refresh, and that's one of the key benefits of the smart cut, because with the refresh we can reuse. And so we can reuse the donor wafer several times, and typically with one donor wafers we create 10 SmartSiC wafers. 1 to 10. So this refresh is a great opportunity for the product to have a greener electronics. Doing some mono SiC, you need to grow a ball. So SiC world is totally different from the silicon conventional ingot. When to grow a ball, high temperatures, very long times, and at the end, roughly 50 wafers per ball. With the SmartSiC, we can consider these materials. It gives the donor wafers. We have a quite quick and easy CVD process to create poly SiC. We associate with refresh, meaning that with one ball, we generate roughly 500 SmartSiC wafers. So, a strong improvement in the availability regarding the availability of the product, and significant improvement in the CO2 emissions for the product. Material engineering is needed, of course, to create the ultra-low resistive poly SiC. Here, a few pictures. We can have, with CVD, a very large choice of microstructures for the SmartSiC product. So we have to adapt. We have to adapt the poly SiC to have real wafers. And at the end, we obtain wafers able to be handle wafers for our product with very low resistivity, which is key for the product performance. And as I said before, we divide by a factor of 10 the handle wafer resistivity, from 20 to less than 2 million centimeters. Maybe I need to speed up. When you combine a mono SiC, a perfectly conductive bonding layers, and the handle wafers, bonding interface has ohmic behaviors, strong resistivity improvement. We can monitor, of course, the total substrate electrical resistivity, and we confirm also this electrical resistivity is stable, whatever the temperatures, from the room temperatures. Okay, now it's nice, but also the device operating temperatures. Typical power device operate at 175 degrees. And so we have, in both cases, a very low electrical resistivity for the substrates, and so at the end, a significant improvement on the radiation of the power device. Again, okay, it's good for SmartSiC performance product. When we move to SmartSiC Advanced, in addition, we had crystal engineering, and so we demonstrate that we can deliver a BPD-free materials. So we know SmartCut, in principles, does not add any crystal defect on the transfer layers. We confirm, here we have nice pictures, we confirm on SiC, if you compare with KOH decorations, if you compare the crystal defect mapping on the donor wafers on exactly the same position, the crystal defect mapping on the SmartSiC, you find exactly the same crystal defect. We do not generate, we do not change the crystal. So now we prepare, we improve the donor wafers, we generate a BPD-free layers on the donor wafers, and we can transfer these BPD-free layers. And so it means that on the so-called Gen 2.2 SmartSiC Advanced, okay, we do not change the defect density of dislocation, but for the BPD basal plane dislocations, which has a significant impact on the device reliability, we are at 0. All this development has been engaged first with 6-inch. Wafers are more available, but we also demonstrate in 200 millimeters. SmartCut technology is not limited by the wafer diameters, and so we already engaged some 200 millimeters and some 200 millimeters SmartSiC wafers are now in some customer lines under evaluations. And so that's a nice development. Engineering substrates, it's interesting to develop, but we also now combine the material engineering on the path to the market deployment, building our fab. And if you visit Grenoble area in Berlin, you will find a new fab. We call it Berlin 4, under constructions now on opening next spring in April. So the first wafers out of this new fab is scheduled in July next year. Thank you.
Thank you, just in time. We have time for a question.
Thank you very much. Please use the microphone because of the filming.
Yeah, thank you. Could you please spell the BPD acronym?
Basal plane dislocation.
Basal plane dislocation. Thank you.
Anything else from the Swedish side, maybe? How about you students? Are you awake today? Where are the students? Hands up. Whee! You're not curious to know anything more? Not right now. That's fine. You can also talk to our speakers during the break, of course.